Hello students. So from today onwards we are going to revise chapter 2, 5, 6 and chapter number 10 for the first terminal exam. Okay. Now for the first terminal exam you have been given question bank. So please go through the question bank. If there is doubt in question bank, please let me know. Okay. So from today we are going to have a revision session. So today we are going to discuss chapter number 2. Okay, so chapter number 2 is solutions. So in today's video we will discuss what are the important topics and what should be the appropriate answer for the given question. Okay, so the chapter solution starts with definition. What is solution? So solution is a homogeneous mixture, right? Which comprises either two components or more than two components. Okay. Then there is classification of solution based on physical state. So there are three classes of solutions: solid solution, liquid solution, and gaseous solution. Then chapter deals with different types of concentrations. Okay. So we'll revise the formulas. First is molarity. So molarity is mole per liter, right? We know the formula of molarity, mole per liter. So formula will be weight of solute divided by molecular weight into volume of solution. So if volume of solution is in ml, then you need to multiply it by 1000. So this is molarity, which is indicated by capital M. Then molality, which is indicated by small m. So molality is weight of solute divided by molecular weight into weight of solvent, which is in gram. Then you need to multiply it with 1000. Okay. Next formula is percentage weight by weight. So percentage means mass of component divided by total mass, and this is percentage, so you need to multiply it with 100. Same way, the formula of mass percentage weight by volume is mass or weight of component upon total volume of solution, total mass of solution or total. Then percentage volume by volume is equal to volume of particular component upon total volume into 100. Okay. Then ppm. ppm is parts per million. So part of any component, the one part of any component divided by total parts of component, total parts of solution into 10⁶. So parts per million means parts of any component divided by total parts of solution multiplied by 10⁶. Then one more formula, that is mole fraction. So mole fraction is equal to moles of any component, mole of component. So I am writing in short form, mole of component divided by total mole of components divided by total mole. Okay. So mole of particular solute or solvent divided by total mole. Total means moles of solute plus moles of solvent. Okay. So this is mole fraction. So these are the important formulas which you need to remember for the concentration terms. Now the chapter deals with solubility. Next topic is solubility. Okay. So solubility is given in two terms: solubility of solid in liquid and solubility of gas in liquid. Chapter deals with two types of solubility: solubility of solid in liquid and gas in liquid. If you have been asked to write about solubility of solid in liquid, then which are the main points you need to discuss? You need to discuss about solution, types of solution, saturated, unsaturated solution, saturated and unsaturated solution. You need to discuss about crystallization. You need to discuss about dissolution and which type of solid dissolves in which type of solvent. So as we know, polar solute dissolves in polar solvent, non-polar solute dissolving non-polar solvent. Okay, so types of solute plus types of solvent. So these are the important points you need to write for the answer of this question. Now, for the solubility of gas in liquid, which is again known as Henry's law. So if this question is there in exam, then you are supposed to write main points like, first, what is Henry's law? Okay, so statement of Henry's law. Then formula of Henry's law, and formula is P is equal to AH into X. Partial pressure of solution is directly proportional to mole fraction, where KH is Henry's constant, right? Okay, and Henry's constant is different for different gases. Okay, if this question is of 3 marks and you have been asked to write applications, then you need to mention applications of Henry's law. And there are 3 applications. First application, which talks about CO2, solubility of CO2 in cool drink, right? Second application is of scuba divers. Third application talks about higher altitude. So these 3 applications should be written. Okay, so if there is application term, right? If you have been asked to write application, then you need to discuss these 3 applications. Okay. Now, after this topic, chapter deals for Raoult's law. Chapter deals with Raoult's law. And there are 2 types of Raoult's law, right? Do you remember the Raoult's law? And Raoult's law are of 2 types. First Raoult's law is for volatile solute. Second Raoult's law is for non-volatile solute. Non-volatile solute. In these 2 cases, solvent is volatile. Solvent is volatile. Now what does it mean? Volatile means the liquids which can be converted into vapor form easily, right? Okay. Now, Raoult's law for volatile solute, then you need to write this formula, or you need to derive this formula. P total is equal to P1 plus P2. So first of all, you need to write the statement of Raoult's law for volatile solute. The partial pressure of solution or partial pressure of component is directly proportional to mole fraction of individual component, right? Partial pressure of any component is directly proportional to mole fraction of that component. Okay. So Raoult's law for volatile solute, which means in solution there is volatile solute plus volatile solvent. So the total vapor pressure is equal to summation or addition of partial pressure of individual component, or we can say that partial pressure of solid plus solvent. And please remember, in this whole chapter, one number is designated for solvent and two number is designated for solute. Okay. Then this formula is P total is equal to P01 P1 plus P01 X1, sorry, P01 X1 plus P02 X2. Okay. So this formula you need to derive. Then you need to draw graph for Raoult's law. Now for Raoult's law for non-volatile solute, you need to discuss the difference between solvent and solution and why the vapor pressure of solution decreases with compared to solvent. And you need to write this formula. Pressure is directly proportional to mole fraction. So pressure is equal to, or we can say P1 is directly proportional to X1. Then P1 is directly proportional to P01 into X1. So for non-volatile solute, you need to discuss this formula. Okay. Now, after Raoult's law and after Henry's law, there are many numericals. So you need to look at the numericals which concern with Henry's law and Raoult's law. Okay. So please let me know if there is doubt in any numerical. Okay. Now, so after Raoult's law, the topic is ideal solution and non-ideal solution. Ideal and non-ideal solution. Okay. So mostly the question can be asked like this: differentiate between ideal and non-ideal solution. Or question can be like this: write difference between ideal and non-ideal solution. So normally this question can be asked in 2 marks or 3 marks. So first of all, you need to discuss what is ideal and what is non-ideal solution. Okay. So the solution which follows Raoult's law, that is ideal solution, and which does not obey Raoult's law, that is non-ideal solution. So here Raoult's law is obeyed. Here Raoult's law is not obeyed. Right? Then difference is like delta H is equal to 0, delta V is equal to 0. Here delta H is not equal to 0 and delta V is not equal to 0. Okay. Then you need to discuss about interaction. The interaction like two components. If component A and component B is there, then after mixing, there is another interaction, that is AB, and AA BB is equal to AB. Whereas in this case, AA interaction, BB interaction is not equal to AB interaction. Okay, you must be knowing about this. I am only discussing. Okay, then there are two situations: positive deviation and negative deviation. Okay, so you need to discuss all these things along with examples. Example of ideal solution and non-ideal solution. Okay. Now, after this topic, there is one topic, that is azeotrope properties. So what is colligative property? So colligative property is the property which depend on the amount. So which is quantitative property, or which deals with amount of solid. Okay. So there are 4 properties. First is relative lowering in vapor pressure. Relative lowering of vapor pressure. Second one is elevation in boiling point. Elevation in boiling point. Third one is depression in freezing point. Depression in freezing point. Fourth property is osmotic pressure. So there are total 4 properties which are known as qualitative properties. Now this question is mainly important for numerical. So you need to write formulas of each and every qualitative property. Okay. So formula for relative lowering in vapor pressure is P01 minus P1 upon P01 is equal to Wm mw. Remember, I had taught you shortcut to remember this formula. Wm mw 2121. So 2121. Wm mw 2121. Okay. Now elevation boiling points. Delta Tb is equal to Kb into m. Delta Tb is change in boiling point. Kb is molar elevation constant and m is molality. Formula for freezing point is delta Tf is equal to Kf into m, where delta Tf is equal to change in freezing point, Kf is equal to molar depression constant and m is equal to molality. Now formula for osmotic pressure is equal to pi is equal to CRT, where pi stands for osmotic pressure, C stands for concentration, R is gas constant, and T is temperature. Another formula is pi is equal to WRT by MV. Weight of solute, gas constant, temperature, molecular weight of solute, and volume of solution. Okay. So please remember all these formulas. These formulas are important for numerical purpose. Okay. Now, the last topic of this chapter. The last topic of this chapter is abnormal molar mass. Abnormal molar mass. Then you need to remember what is one-top factor. What is one-top factor? Okay. The formula of one-top factor, and this topic is again important for numerical purpose. The numerical of dissociation, the numerical of association, the numerical for the calculation of acid dissociation constant, the numerical for the calculation of alpha, which are important numericals. So please go through the numericals. If there is any doubt in this kind of numericals, please let me know. Okay. So the chapter 2 solution deals with all these topics. So I have discussed these topics in very brief. If you have any doubt in if you have any doubt in any topic, please let me know before exam. Okay. Thank you.
Volume by volume percentage and mass by volume percentage are functions of temperature. This is because volume is a temperature dependent quantity, while mass is independent of temperature. Solubility is the property of a solute to dissolve in a solvent to form a homogeneous solution. Solubility is defined as the maximum amount of solute that can be dissolved in a specified amount of solvent at a specific temperature. Solubility is the result of an interaction between particles of the solute and the solvent. Hence, it depends on the nature of the solute and the solvent, as well as on the temperature and pressure. However, note that the solubility of solids in liquids is independent of pressure. Let us first discuss the solubility of solids in liquids. The solubility of solids in liquids depends upon two factors, namely, the nature of the solute and solvent, and the temperature. Let's discuss how solubility depends on the nature of the solute and solvent. It is observed that while sodium chloride and sugar dissolve readily in water, naphthalene and anthracene do not. In general, solubility follows the rule like dissolves like. That is, a polar solute dissolves in a polar solvent, and a non-polar solute dissolves in a non-polar solvent. Therefore, polar or ionic molecules like sugar and sodium chloride dissolve in water molecules which are polar, while non-polar molecules like naphthalene and anthracene dissolve in solvents like benzene and carbon tetrachloride, which are non-polar. This behavior can be explained in terms of the interaction between particles of the solute and the solvent. The solubility of ionic compounds is the result of the strong electrostatic interaction between the ions of the solute and the polar molecules of the solvent. The solubility of non-polar solutes is the result of similar solute-solute, solute-solvent, and solvent-solvent interactions. When a solid solute is added to a solvent, its concentration in the solution increases. This process is known as dissolution. If you continue to add the solute, there will come a stage when no more of the solute can be dissolved in the solvent at a given temperature. A state of dynamic equilibrium is reached between the solute particles going into the solution and the solute particles separating out. Such a solution, in which no more of the solute can be dissolved at a given temperature, is called a saturated solution. Therefore, a solution in dynamic equilibrium with undissolved solute is a saturated solution and contains the maximum amount of solute dissolved in a given amount of solvent. The concentration of the solute in such a solution is its solubility. If any more solute is added to this saturated solution, it gets separated out, and the process is called precipitation. On the other hand, a solution in which more solute can be dissolved at a specific temperature is called an unsaturated solution. The solubility of a solute also depends on temperature. When a solid dissolves in a liquid, a change in the physical state of the solid takes place. Heat is required to break the bonds holding the molecules in the solid together. At the same time, heat is given off during the formation of new solute-solvent bonds. If the heat liberated in the dissolving process is greater than the heat required to break the solid apart, the net dissolving reaction is exothermic, as energy is given off in the process. It can be seen that as per Le Chatelier's principle, for an exothermic dissolution process, an increase in temperature inhibits the dissolving reaction, since excess heat is already being produced by the reaction. For salts like cerium sulfate and sodium carbonate monohydrate, an increase in temperature decreases solubility. On the other hand, if the heat given off in the dissolving reaction is less than the heat required to break the solid apart, the net dissolving reaction is endothermic. As per Le Chatelier's principle, for an endothermic dissolution reaction, more heat facilitates the dissolving reaction by providing energy to break the bonds in the solid. The solubility of most substances like sodium nitrate, sodium chloride, and potassium nitrate increases with an increase in temperature. The use of first aid instant cold packs is an application of this solubility principle. Ammonium nitrate is used in instant cold packs as its hydration is an endothermic process. That is, it requires heat. Therefore, heat is drawn from the surroundings and the pack feels cold. Note that the solubility of solids in liquids is independent of pressure, since solids and liquids do not compress appreciably when the pressure is increased.
Gases dissolve in liquids to form solutions. Generally, gases that are easily liquefiable are more soluble in a solvent. For example, carbon dioxide is more soluble in water than oxygen at a given temperature. Oxygen dissolves in water to a very small extent, about 5 to 10 milliliters per liter of water. However, even this small quantity can sustain aquatic life. The dissolution of gases in liquids is an equilibrium process. At equilibrium, the rate at which the gaseous solute molecules escape the solution equals the rate at which the molecules re-enter the solution. An increase in pressure results in more molecules of the gas striking the surface of the liquid and entering the solution in a given time. Therefore, at high pressure, more gas dissolves in a given volume of liquid than at lower pressures. This proportionality of the solubility of a gas to pressure was first proposed in 1800 by William Henry and is known as Henry's law. The law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas. Dalton, a contemporary of Henry during the same period, concluded independently that the solubility of a gas is a function of its partial pressure. If the solubility of a gas is expressed in terms of the mole fraction, then the statement of Henry's law becomes: the mole fraction of a gas in a solution is proportional to the partial pressure of the gas over the solution. However, the most commonly used version of Henry's law is: the partial pressure of a gas in vapor phase, P, is proportional to the mole fraction of the gas, X, in a solution. Mathematically, it can be represented as P is proportional to X, or P is equal to KHX, where KH is the Henry's law constant. Further, if you plot a graph between P, the partial pressure of a gas in vapor phase, and X, the mole fraction of the gas in a solution, then you will get a straight line passing through the origin with its slope equal to kh. The graph also shows that as P increases, X, the mole fraction of the gas in a solution, also increases. The Henry's law constant, kh, for some common gases and water as the solvent are given in the table here. On comparing the values of Henry's constant for oxygen